Hello, everyone, and welcome to Lecture 7. So, Chem 152, Lecture 7 on colligative properties. This covers OpenStax section 10.4, and this is the final lecture of Unit 1. First, what are colligative properties? Colligative properties are defined as the properties of solutions that depend on the ratio of solute particles to solvent molecules, i.e. concentration, and not on the type of chemical species present. So what this means then is this is solely about the ratio of solute particles to solvent molecules. It does not matter necessarily what the identities of these solute particles or these solvent molecules are. It's strictly about the mathematical ratio between these two species, the solute particles and the solvent molecules. Colligative properties are essentially the properties of the solvent which are changed by the presence of the solute particles, because the presence of these solute particles will disrupt the intermolecular forces that are holding these solvent molecules together. I do want to note that the term colligative here is derived from the Latin term colligatus, which means bound together. So colligative properties are properties, again, of the solvent, and these solvent properties are changed because they are being disrupted by the presence of those solute particles. So thinking back to what we discussed last lecture with regard to the way that solutions are formed, right? When you have those solute-solvent interactions, that's kind of what's going on here, is that those interactions are going to change the properties of the solvent. So there are the number of dissolved solute particles is what ultimately affects the properties of the solution. All the properties below are affected, again, by the number of particles of dissolved solute. The four we're going to look at today are vapor pressure, boiling point, osmotic pressure, and freezing points. The number of particles of dissolved solutes depends, however, on how that solute dissolves. And so in this way, the identity of the solute does make a little bit of a difference, right? Whether or not the solute is a molecular compound or if it's an ionic compound. But the identity of the compound here is really just being used to understand how many solute particles we have. A molecular compound, so what could be described as a non-electrolyte, so a non-electrolyte like C6H12O6, this molecule, when it dissolves in water, as we learned, it does not ionize. So the C6H12O6 stays together and just becomes an aqueous molecule. Whereas with an ionic compound, something like sodium chloride, though we initially have one molecule, when it's dissolved and it becomes part of a solution, we now have two molecules. So molecular versus ionic is going to affect the number of particles dissolved. So we can quantify this with something called the Van 't Hoff factor. So molecular compounds have a Van 't Hoff factor of 1. It's basically non-electrolytes. Van 't Hoff factor, which is defined by the variable I. They have a Van 't Hoff factor of 1. And the 1 here just means that you have one dissolved particle, essentially. With something like an ionic compound, or basically electrolytes, your Van 't Hoff factor I is defined as the number of ions formed upon dissociation. So sodium chloride here, for example, would have a Van 't Hoff factor of 2. It forms 2 ions upon dissociation. So we can see here like ethanol and benzene, which are molecular compounds, so they are non-electrolytes, have Van 't Hoff factors of 1. Lithium bromide, similar to sodium chloride, when it dissolves, would form 2 ions, so it has a Van 't Hoff factor of 2. Sodium sulfate, 3. Magnesium chloride, 3. Calcium nitrate, also 3. Something like sodium phosphate would actually have 4 ions when dissolved. You'd have 3 sodium ions and the phosphate ion, so it'd have a Van 't Hoff factor of 4. What about aluminum sulfate? What would the Van 't Hoff factor for this be? You should be able to quickly recognize that it would have a Van 't Hoff factor of 5. If this thing dissolved in solution, you'd get 2 aluminum ions, 3 sulfate ions for a total of 5 ions, so a Van 't Hoff factor of 5. So again, to reiterate, molecular compounds, or those that are non-electrolytes, form 1 ion upon dissociation, or actually, I should say, don't form any ions upon dissociation. They have just one molecule dissolved in solution. Their Van 't Hoff factor is 1. Anything that's an electrolyte, which would primarily refer to ionic compounds, but could also refer to strong acids and bases, their Van Hoff factor would be based on the number of ions formed upon dissociation. All right, next. As mentioned, colligative properties, they depend on the number, not the identity of the particles dissolved in solution. So sodium chloride, magnesium sulfide are examples of molecules where the Van Hoff factor is 2. To determine the total number of particles in the solution, you need to take the concentration you are given, whether this is a molarity, a molality, or a mole fraction, and you need to multiply that concentration by the Van Hoff factor. This is how, again, you properly determine the number of particles in the solution, as we're going to relate this value to their effect on the colligative properties. So as the number of particles in the solution increases, 2 of those properties we mentioned will increase, 2 will decrease. So boiling point and osmotic pressure will increase as the number of particles in solution increases. Freezing point and vapor pressure will decrease. And we're going to break down the reasons why when we get to each of these properties. We're going to start with vapor pressure. Vapor pressure and how vapor pressure changes is related by Raoult's law. And so Raoult's law is defined as P, pressure, equals X solvent. And remember this kind of cursive looking X here stands for mole fraction. So this is the mole fraction of solvent in solution times P0. P0 is defined as the vapor pressure of the pure solvent. So the vapor pressure of the solution equals the mole fraction of the solvent multiplied by the vapor pressure of the pure solvent. And again, X mole fraction is moles of one component divided by total moles of all components. So for our purposes, this would be moles of solvent on top divided by moles solvent plus moles solute particles. Just don't forget to multiply the moles solute particle by the Van Hoff factor for that solute. All right, now, why do fewer solvent molecules escape from the surface of a solution than of a pure solvent? Remember what we said here previously, or on the previous slide, that as the number of solute particles increases, vapor pressure decreases. So why then? Why do fewer solvent molecules escape from a solution than of a pure solvent? Analyze these 2 diagrams for a second and think about the solute-solvent interactions. Pause the video, see if you can come up with an answer, and then I'll explain the answer. All right, so the answer here is quite simply, it's those solute-solvent interactions that prevent or block the solvent molecules from escaping. So if we look at the image here of the pure solvent, we can see then there's nothing in their way. These pure solvent molecules, they can simply escape once they have enough energy to break away from the intermolecular forces. They can simply and easily escape from the liquid phase into the gas or the vapor phase. There's nothing in their way. Whereas when we've got a solution, these solvent molecules, yes, they need to overcome the intermolecular forces that are holding them together, but we also have those solute-solvent interactions, right? And so for these solute particles to even dissolve, those solute-solvent interactions must be stronger than the solvent-solvent interactions, right? We kind of learned about that in the previous lecture when we were discussing how solutions are formed when we thought about the enthalpy change here. So the solute-solvent interactions are likely stronger than the solvent-solvent interactions are. So we've got that to deal with, and we've also got the fact that it's just more molecules in the way. And so it's harder for these solvent molecules to escape. And so if it's harder for them to escape, fewer escape. And so we therefore get a lower vapor pressure as the number of solute particles increases. Hold on, my slides are stuck. There we go. All right, so let's go over a practice problem. Calculate the vapor pressure of a solution made by dissolving 218 grams of calcium nitrate in 500 milliliters of water at 30 degrees Celsius. The vapor pressure of pure water at 30 degrees Celsius is 31.82 torr. Assume the density of water is 1 gram per milliliter. Okay, so right away, if you're being asked to do a vapor pressure problem, you should recognize here that we are using Raoult's law. So P stands for vapor pressure of the solution equals X solvent, mole fraction of the solvent, times P0, which is the vapor pressure of the pure solvent. You see some temperature values mentioned here. This is not a Clausius-Clapeyron equation. You don't need to make use of these temperature values. It's just important to note here that the vapor pressure of water would change if the temperature changed, but for our purposes, this is what we need. Here it says the vapor pressure of pure water. So our solvent here is water, so this is our P0 value. 31.82 torr is our P0. All right, now let's walk through a couple steps. First, let's solve for the mole fraction of the solvent. So we need to find moles solvent, and then we also need to find moles solute. Okay, so starting with moles of solute. So we're given 218 grams of calcium nitrate, and so I'm showing this work over here. 218 grams divided by the molar mass of calcium nitrate, which is approximately 164.1 grams per mole. This gives a mole amount of 1.3285, and I'm keeping an extra sig fig or two here. 1.3285 moles. This is moles solute, so this value right here is going to go here in our equation. Next, I'm going to calculate moles of solvent. So we have 500 milliliters of water. Right here, it says assume the density of water is 1 gram per milliliter. So 500 milliliters gives us 500 grams of water. I'm going to multiply it by the molar mass of water, which is 18.015, and this gives me 27.755 moles of water. Now I can set up my equation. X solvent equals moles of solvent, so that's the 27.755 moles up top, divided by moles solvent, so this value goes on here on the bottom again, plus I times moles solute. Remember, when you're calculating this mole fraction, you need to account for the Van Hoff factor I with the moles of the solute. So we found that there's 1.3285 moles solute, but we also need to analyze what our Van Hoff factor is. If we look at our compound, it's calcium nitrate. If calcium nitrate dissolved in water, you would see 3 ions form. 1 calcium 2 plus ion and 2 nitrate ions for a total of 3. So the Van Hoff factor here is 3. So that gets plugged in right here. This gives us a mole fraction of 0.8744. And so then our final step is to solve for that vapor pressure of the solution. So the vapor pressure of the solution equals that mole fraction we just found multiplied by the vapor pressure of the pure solvent, which was 31.82 torr. And our final answer is 27.8 torr. This is the correct answer here. I'm rounding the final answer to 3 sig figs, given that this value and this value were both given in 3 sig figs. 27.8 torr. All right, next, boiling point. Now, let's think for a second here. If the vapor pressure of a solution is lower than that of the pure solvent, do you expect the boiling point of the solution to increase, decrease, or remain constant with respect to the boiling point of the pure solvent? Think about this one for a second. Okay, so the correct answer here is the boiling point increases. Remember, so on a couple slides ago, we discussed how vapor pressure decreases, boiling point increases. We can see that here with this graph. And so here we're looking at a phase diagram. So here, this red line, the solid red line, I should say, represents the normal boiling point of, well, I should say it's the phase boundary between the liquid and the gas for the pure solvent. And so we just saw how vapor pressure increases when you add solute into the mix. So vapor pressure increases, then this graph basically should be, is going to slide slightly to the right. So think about this, right? If the vapor pressure is decreasing, that means then that it's going to take longer for the vapor pressure of the solution to equalize the atmospheric pressure, right? Remember that boiling point is defined as the point at which the vapor pressure of your compound, your solution, solvent, whatever it is, when the vapor pressure is equal to the atmospheric pressure. So if vapor pressure is being lowered, it's going to take us longer, or in this case, it's going to require a higher temperature. It's going to require more energy to get the vapor pressure and the atmospheric pressure equal to one another. And so we can see then with this dashed line represents the phase boundary of the solution. So we can see then that the normal boiling point of the solution is slightly to the right, so it's slightly higher than the boiling point of the pure solvent. So the normal boiling point of the solution is higher than that of the pure solvent. And so we call this boiling point elevation. Okay, and then what I just explained is summarized in the text here. All right, so the equation we use is this one, delta TB. So delta TB stands for the change in boiling point above the boiling point of pure solvent. So these values should always be positive, equals KB times I times M. So the I times M, I here, again, is the Van Hoff factor. M with the little underline, the lowercase m with the underline is molality. So remember, molality is moles solute over kilograms solvent. And then that capital KB there is the boiling point elevation constant, which is typically in degrees Celsius per molal. Okay, so let's go through an example problem. This one states, find the boiling point of a solution prepared by adding 96 grams of sodium chloride to 450 milliliters of water. The boiling point elevation constant for pure water is 0.52 degrees Celsius per molal. Let's walk through the work here. So first it says find the boiling point of a solution, which means I'm going to be using this equation, delta TB equals KB times I times M. All right, the boiling point elevation constant for pure water is 0.52 degrees Celsius per molal. So this value right here is going to go with KB. I, the Van Hoff factor, will come from our compound here, our solute, sodium chloride, and then M molality, we're going to need to solve for that. So remember that molality is moles solute over mass of solvent in kilograms. So let's work this out. We have 96 grams of sodium chloride, and sodium chloride here is the solute. Okay, sorry about that. I just had to pause for a second to fix a few of my animations. Okay, so back to where I was. 96 grams of sodium chloride, that's our solute. So we're going to calculate moles solute. 96 grams here of sodium chloride multiplied by the molar mass of sodium chloride. So 1 mole over 58.44 grams. This gives us 1.64271 moles of sodium chloride. Then we're going to find the mass of solvent. So our solvent here is water. So we've got 450 milliliters. We're again going to assume that its density is 1 gram per milliliter. So we'll convert from milliliters to grams by multiplying by 1 gram over 1 milliliter. Then I'm also going to convert from grams to kilograms, right? See here that milliliters would cancel, grams would cancel. This would give my answer in kilograms, and I get 0.450 kilograms. So I didn't show this step in the calculation, but what I did is this value got plugged in here, and this value got plugged in here, and this gave me a molality of about 3.65047 molal. So I can plug my values in now. Delta TB equals, remember KB, the boiling point elevation constant for your solvent, which here is 0.52 degrees Celsius per molal, multiplied by I, the Van Hoff factor of the solute, which for us in this problem would be 2. Sodium chloride would form 2 ions in solution, multiplied by the molality, which we again just found to be 3.65047. This gives us a delta TB of 3.8 degrees Celsius. Now you're not quite done yet. Remember that the question said, find the boiling point of a solution. What we have found is we found the boiling point elevation, or the change in the boiling point. So what we should do then is we should take the boiling point of our pure solvent, which was water, 100 degrees Celsius, and add that boiling point elevation. So 100 degrees Celsius plus 3.8 gives a final answer of 103.8 degrees Celsius. This is your final answer. Do not give this as your final answer. If you're asked to find the boiling point of the solution, do not give this as the final answer. This is the boiling point elevation. you need to take this value and add it to the boiling point of whatever the solvent is. It may be water, it may be a different solvent. If it's a different solvent, the boiling point will be given, and so just pay attention to the information given in the problem and add whatever you get for delta TB to whatever the boiling point of that solvent is to get your final answer. All right, next, freezing point. A few questions. Why do we salt roads to prevent them from icing over? Why should you use antifreeze in your radiator instead of pure water? Or why does a bottle of vodka stay liquid when you put it in the freezer? We're going to answer these questions. So when a substance starts to freeze, those molecules, they lose kinetic energy, they slow down, and the intermolecular forces take over, right? So think about water. When you go from a liquid to a solid, when you put, some water in the freezer, what's going on there is the freezer is cooling the water down, so the movement of those molecules are slowing down. So as the movement of molecules gets slower, the intermolecular forces begin to win, so to speak, right? So those molecules, those water molecules begin to pack into that ordered crystal structure. The molecules arrange themselves in a pattern, typically a crystal lattice, and this turns them into a solid. However, if a solute is present, the solute particles interfere with the intermolecular forces of the solvent, and therefore they interfere with the formation of the crystal lattice. So quite simply, the solute molecules, once again, or the solute particles, I should say, are really just getting in the way. They get in the way of those solvent molecules packing together and forming that nice orderly pattern, that crystal lattice. And so because of this, the solution must be cooled down even further. You need to remove even more energy to slow these molecules down further to get them to pack together and form that crystal lattice. So thus, we see then that a solution requires a lower temperature to freeze. Freezing point decreases, or we call this freezing point depression. And you can see it on this curve right here. The dashed line here represents the normal freezing point of the solution. The solid line represents the normal freezing point of the pure solvent. So you can see the solution, the line is moved slightly to the left. And from here, we can see then that this solution, it crosses the 1 atmosphere line at a lower temperature than the solvent does, thus freezing point depression. This is part of the reason why we salt roads, why we use antifreeze, or why vodka stays liquid in the freezer. Vodka is not pure water, right? It's a mixture of ethanol and water, and so thus its freezing point drops because it's a mixture, it's a solution. Freezing point depression, it has a very similar equation to what we just saw with boiling point elevation. It's delta TF equals KF times I times N. Delta TF is again the change in freezing point. Important to note here that it's below the freezing point of pure solvent. So your delta TF value will again end up being positive. You're just going to have to subtract it from the freezing point of the pure solvent instead of adding like you did with boiling point. M is molality, I is the Van Hoff factor, and Kf is the freezing point depression constants. Let's look at an example problem. The main component of antifreeze is the organic compound ethylene glycol, which is its formula is HOCH2CH2OH. Find the concentration of ethylene glycol in water needed to drop the freezing point of the water by 2.64 degrees Celsius. The Kf of pure water is 1.86 degrees Celsius per molal. So this one, a little different than the previous problem. See right here, it says find the concentration needed to drop the freezing point of the water by 2.64 degrees Celsius. So we're doing something a little bit different. Let me go through here. Okay, so what we are solving for, in fact, is molality. See, it says find the concentration of ethylene glycol in water. So concentration is molality. So we're actually solving for molality, M here. So I take this equation and rearrange it to solve for M. This gives me delta TF over KF times I. So now we can plug some variables in. Our delta TF value was 2.64 degrees Celsius. Our Kf value was 1.86 degrees Celsius per molal. And our value for I, the Van Hoff factor, is going to be 1. See how it says it's an organic compound. Organic basically means a molecular compound, meaning it's a non-electrolyte, and its Van Hoff factor would be 1. When you plug this in and solve, you get a molality of 1.42. So 1.42 molal is the correct answer here. Okay, a few special notes on I, Kf, and Kb. Again, reminding you that the Van Hoff factor I is based on the number of solute particles in solution. It is not affected by the solvent. However, Kf and Kb are specific to the solvent used, not to the solute. So these two things are independent from one another. Van Hoff factor I is purely based on the solute, whatever the solute is, and it's not affected by the solvent. But on the flip side, Kf and Kb are specific to the solvent and don't have anything to do with the solute. Here's a few example Kf and Kb values. You're not going to be expected to memorize these. They would be given in the question, so you can use them as they are needed. I just wanted to emphasize again that I is related to the solute, whereas Kf and Kb are related to the solvent. Let's quickly analyze this freezing point depression discussion. So as I'm recording this, just last week, we had a snowstorm here in Raleigh, North Carolina. So this is particularly relevant. So in the winter, many states will salt the roads with either a brine solution or gritty salt to de-ice the roads. Why does salt work to de-ice the roads? And second question, at extremely low temperatures, would a salt with a higher or lower I value be more effective at de-icing, and why? So pause the video for a second, see if you can answer these two questions. Okay, answer to the first question, why does salt work to de-ice the roads? Well, as we just saw, when you add solute to solvent, right, so if we think about, some snow or some ice falling on the roads, it's mostly water, right? I'm sure there's some minerals, some different ions in it, whatever else is going on in there. So it's not pure water, but it's mostly water. And so water generally freezes around 32 Fahrenheit or 0 degrees Celsius. Now, if we add salt to the roads, so basically we're adding salt to that water, to that snow or to that ice, we're lowering the freezing point of that water on the roads in the form of snow or ice. So if water's normal freezing point is around 32 Fahrenheit and we add a lot of salt to the roads, maybe we are able to drop that freezing point to 26, 27 degrees Fahrenheit. So if it's 30 degrees outside and it's snowing and you salt the roads, thus lowering the freezing point of the water down to 26 or 27, what you've done basically is you effectively lowered the freezing point of water below that of the current conditions. And so this allows then the snow or the ice to melt and to keep the roads, safe and drivable, even if, the current temperature is still at or below freezing. Now, when you get down to really low temperatures, this will begin to lose its effectiveness because it becomes harder to basically beat the outside temperature. If it's 10 degrees Fahrenheit outside, you'd have to add a lot of salt to the roads to lower water's freezing point that far. But at extremely low temperatures, would a salt with a higher or lower I value be more effective? You should note here that a salt with a higher I value would be more effective, because if you have a higher I value, you're going to lower the freezing point more. Okay, let's practice with freezing point depression. Arrange these solutions in order of decreasing freezing point. So go from the highest freezing point to the lowest freezing point. So I would again encourage you to pause the video for a moment and see if you can come up with the correct answer here. Okay, so I'm going to go over this one now. To be able to answer this question, we first need to analyze two things. What is the concentration of the solute here, which in this case would be these compounds highlighted in purple, and importantly, what is their Van Hoff factor? So I'm going to multiply those two things together. I'm going to multiply the concentration of the solute by the Van Hoff factor of the solute, and then arrange from there. All right, so because these are all aqueous, we assume they're all in water, so they all have the same Kf. So delta T is purely related to I times M. A larger I times M is going to give us a lower freezing point. So sodium phosphate here, we have a concentration of 0.10 molal and a Van Hoff factor of 4, which gives us an effective concentration of 0.40 molal. Sodium chloride has this solution, concentration 0.25 molal and a Van Hoff factor of 2, giving us an effective concentration of 0.50 molal. This magnesium chloride solution has a concentration of 0.20 molal. This would give us a Van Hoff factor of 3, so an effective concentration of 0.60 molal. And then finally, glucose, C6H12O6, This is an organic compound. It's a non-electrolyte. Its Van Hoff factor would be 1, giving an effective concentration of 0.15 molal. So to arrange these in order from highest freezing point to lowest, D would have the highest freezing point because it has the lowest concentration, then A, then B, then C. So you're basically ordering these from lowest concentration to highest, because the higher these concentrations are, the bigger delta TF is going to be, and the bigger delta TF is, the lower the freezing point is, the more the freezing point is being lowered, essentially. Okay, here is again an analysis and an overall picture of the phase diagram for a solution. So you can see the solid lines again are the pure solvent, and the dashed lines represent the solution. And so we can see here how the freezing point is depressed, represented here by delta TF, and the boiling point is elevated, represented here by delta TB. All right, last one to analyze is osmotic pressure. So you should be familiar with the term osmosis. So osmosis refers to the diffusion of solvent, typically water, across a semi-permeable membrane. So an example we would have here is we've got this U-shaped tube. We've got pure solvent on the left side, probably water, and then we've got solution on the right side. So we have solvent molecules, which are these little yellowish spheres, and solute molecules, which are these big blue spheres. Now, this semi-permeable membrane is fine enough, or its openings are small enough, that only solvent molecules can pass through. The solute particles cannot. So that's represented here by this little arrow showing that the solute particle would just bounce off the membrane and stay on this side, but the solvent molecules can move through easily. So solvent molecules then will pass through the membrane to the more concentrated side, right? In an effort to equalize the concentration on both sides, you're going to have a net flow of solvent molecules from the left to the right, from the less concentrated side to the more concentrated side. This will continue until the hydrostatic pressure is high enough that the rate of solvent transfer is equal from both directions, right? So in theory, if this was a horizontal tube where gravity wasn't a factor, the solvent would make its way from the left to the right until the concentration on both sides was equal. But we're looking at a U-shaped tube here where gravity is in effect, right? Is in effect, only so much solvent can go through before the pressure from this solution pushing against the membrane is going to become too great. So that's what it means here, until the hydrostatic pressure is high enough that the rate of solvent transfer is equal from both directions. Eventually, you will hit a point where, yes, solvent is going to move from left to right in an effort to equalize the concentrations, but you will also have some solvent moving from right to left simply because there's too much pressure. There's too much solution on the right side pushing on that membrane. And so when that solvent transfer is equal, that's where we define the osmotic pressure. It's when the hydrostatic pressure is high enough that the rate of transfer is equal from both directions. So this is our osmotic pressure. And this osmotic pressure is a colligative property that will change depending upon the identity of the solute. So again, the osmotic pressure of the solution. Osmotic pressure is defined by the capital, this is a capital pi. So this is the Greek letter pi, but it's the capital version. So this pi solution, this is the osmotic pressure of the solution. Again, this is the hydrostatic pressure at which the rate of solvent transfer across the membrane is equal in both directions. It's defined with this equation. The osmotic pressure of the solution equals I times M. So I here is again the Van Hoff factor. M is the molarity of the solution. R is the ideal gas constant, and T is temperature. So osmotic pressure values are often going to be in atmospheres. Molarity M is moles over liters. R is the ideal gas constant, and be careful. Note that in this problem, you are using this version of the ideal gas constant. You're using the 0.08206 liter atmosphere per mole Kelvin. So earlier in this unit, when we were using the Clausius-Clapeyron equation, we saw the other version of the ideal gas constant used, the 8.314 joule per mole Kelvin. So just be careful and make sure you use the correct version of the constant depending upon which equation you are working with. If you're dealing with Clausius-Clapeyron, you're dealing with energy values, you should use the 8.314 version because that version has the unit joule in it, which is the unit of energy. If you're working with osmotic pressure, the key word is pressure there. You should be using this version because this version of the ideal gas constant has a pressure unit in it. Atmospheres, 0.08206 liter atmosphere over mole Kelvin. And finally, T is simply the temperature in Kelvin. Let's look at an example problem. What is the osmotic pressure in atmospheres of an aqueous solution that contains 5 grams of sodium chloride in a volume of 0.750 liters at a temperature of 37 degrees Celsius? All right, so let's work through this. We are being asked to solve for an osmotic pressure, so we're solving for this variable right here. So we need I, M, R, and T. All right, R is the ideal gas constant, 0.08206. M is molarity, I is Van Hoff factor, and T is temperature. So I, the Van Hoff factor here, is 2. It's sodium chloride, NaCl. It would form 2 ions in solution, so I equals 2. Next, I'm going to solve for moles NaCl. Remember that I need to find the molarity of the solution. So to do that, that would be moles solute, which is sodium chloride, over liters solution. So I have 5 grams of sodium chloride. I'm going to multiply by its molar mass. So multiplying by 1 mole over 58.44 grams gives 0.08558 moles sodium chloride. With this, I can solve for the molarity. So I'm going to take that moles NaCl, and I'm going to divide by the volume of the solution, which was given right here, 0.750 liters. This gives a molarity of 0.11408 moles per liter. Now I'm going to take that temperature I was given, 37 degrees Celsius, and I'm going to convert it to Kelvin. The ideal gas constant has units of Kelvin, so my temperature value needs to be in units of Kelvin. 37 degrees Celsius plus 273.15 gives 310.15 Kelvin. Now I can plug everything in. The osmotic pressure of the solution equals the Van Hoff factor, which we found to be 2, times the molarity, 0.11408 moles per liter. And I do recommend keeping the molarity in moles per liter instead of just writing M to make your units cancel properly. Ideal gas constant R, 0.08206 liter atmosphere over mole Kelvin, and temperature T, 310.15 Kelvin. So when we plug this in and solve, if you follow the units, see right here, moles cancel, liters, Kelvin, and Kelvin cancel. The only unit that remains is atmospheres. Makes sense. We're solving for a pressure, and the correct answer here is 5.8. 5.8 atmospheres. All right. Now, you may also be asked to use this equation to determine the molar mass. So all colligative properties are directly proportional to the number of solute particles present in a given amount of solution. If we have a solution prepared using a known mass of solute and solvent, we can measure one of these colligative properties and use it to determine the solute's molar mass. So suppose you were given this question. You have prepared 0.500 liters of an aqueous solution containing 10 grams of an unknown protein. The osmotic pressure of the solution is measured to be 5.9 torr at 22 degrees Celsius. What is the molar mass of the protein? Let's walk through this one. Let's think about a strategy here. All right, so you're given an osmotic pressure. You're told it's 5.9 torr. You're told that this is an unknown protein, and you are told that it's got 10 grams. So what we're going to do here is we've got a temperature, we've got an osmotic pressure. Right here, I see a volume. We're going to be able to use all of these pieces together to solve for molarity. Once we solve for molarity, we can use that molarity and the liters of the solution to solve for moles solute. And once you have moles solute, the protein, you can use that grams value given and those moles value, you solve for to calculate the molar mass. Oh, sorry, I thought I showed the steps here, my mistake. Okay, so to set this one up, you would use the equation outlined on the previous slide, that pi osmotic pressure of solution equals I times m times r times t. This is a protein, so you can assume that it's an organic compound, a molecular compound with an Van 't Hoff factor of 1. You're going to solve for molarity. R is the ideal gas constant and T is the temperature. So use that equation to solve for molarity. Then use the molarity in this volume to solve for moles. Once you solve for moles protein, simply take the 10 grams and divide by that number of moles you found, and that will give you the molar mass of the protein. Okay, so summarizing everything we covered today, vapor pressure uses Raoult's law. P equals X solvent times P0. Boiling point elevation and freezing point depression, very similar equations, delta TB, delta TF, KB, KF, and then both have I times M. Remember that if you're asked to solve for the boiling or freezing point of solutions, that these are just the elevation or depression. So you need to take this and add it to the vapor pressure, or the boiling point of the solvent, or here you would take your delta TF value and subtract it from the freezing point of the solvent. And then osmotic pressure, sorry, my slide got a little messed up here. It's pi solution, or is the osmotic pressure of the solution, equals I times M times R times T. Okay, that is the end of my slides. I've got a couple more practice problems here for you to try, so I would encourage you to try these. So go ahead and pause the video if you'd like to try these problems, and then I'm going to go to the next slide to show the answers. Okay, here are the answers to those 3 problems. That's all I've got in this one, and that's the end of Lecture 7, and it's also the end of Unit 1. Once again, I hope you found this helpful. If you've got any questions, please feel free to reach out to me. I hope you have a great day, and I'll see you in the next one when we start Unit 2.